So let's have a brief chapter about probability and infinite series. As you have seen, there is axiom 3 of probability theory, and yes, and that means that we have infinite series. They are going to be used rather frequently. So here is the first question. Let's see how well you will solve it. Part A, a pair of fair dice is rolled until either the sum of 4 or the sum of 8 appears for the first time. What is the probability that the game is stopped on the sum 8? You understand the question? You have a pair of fair dice. You throw them until you see either 4, the combined sum, or a combined sum of 8. And the question is, and then you stop. And then the question is, what's the probability we stop with 8? So Kazi says 5/8. Let's see what the rest of you are saying. Valeria says 1/2. Naomi says 1/2. Interesting. What about the rest of you guys? Okay, let's see any more comments. Steven says 1/2. Lots of people said 1/2. Shotaro said 1/2. Okay, so shall we, anybody still working on it? Or do we reveal the solution? Okay, so ready, then ready. Here is a solution to part A. So first of all, we can solve this problem in the following way. Let E be the event game ends in a sum of 8. and let E sub n be the event that the game ends with 8 on the nth toss of the two dice. So clearly the intersection between any En and Em is empty set, correct? So that means that by axiom 3 we get an infinite series, which is the summation of P of En. Now for En we can just we can consider the sample space of what can happen if we roll the die n times. We can just restrict to that particular sample space. And first we want to understand how many ways are there to achieve a sum of 8. So this is the way on any particular throw, the sum of 8 is achieved through either 2, 6, 3, 5, and onwards, right? So there are 5 ways of achieving the sum 8. There are only 3 ways of achieving the sum of 4. Yes? Are you with me, guys? So what does it mean? That means that the probability of En is what? So I must miss. You see, you can construct a protocol. What happens if I throw a pair of dice n times, right? What can happen? So each particular throw has 36 outcomes. Now, if I'm getting 8 on the nth trial, that's equivalent to not getting either the sum 4 or the sum 8 for the first n-1 throw of the dice, and getting one of the outcomes that results in 8 on the very last, the nth throw of the die. Are you with me, guys? So therefore, I can write the probability as 36 minus 5 minus 3 divided by 36 multiplied by 5 over 36. So far, what I'm saying, is it logical to you guys? Right? I'm not sure how fast I must go. You see, I kind of, once I'm hoping that you understand the Kafka protocol, I'm not always going to explicitly mention it, right? Only at times, right? But you should always think, how do I get this number? What would be the Kafka protocol for the situation? I can model a special sample space of throwing the die n times. And if I throw the die n times, that means that the pair of dice, to be precise, right? Each particular outcome, each particular box of the throws is 36 possibilities, right? And how many of those possibilities, the first n-1 of those trials resulted in neither success nor failure. That means in 36 minus 5 minus 3 possible outcomes. And the last outcome resulted in success. There are one of 5 possible outcomes, correct? Yes? So, yes, guys, correct? Or, you know, I do not know. Looking at your faces, it's not that always, not that perfectly clear if what I'm saying is right or wrong, especially after the conversation I had this afternoon. A very weird conversation. I have weird people calling. So, naturally, right? No, normal people do not bother calling me, right? Who would? But weird ones, my God, too many. So good, understood, guys?
Yeah, it makes sense.
Wonderful. Thank you for speaking. So that's how I obtained this particular sum. Okay. And then I need to sum this series, and we reviewed series, correct? We reviewed how to add up series. So I just add this stuff up. I add it up. And how do you add it, right? So you see it's a geometric series, and the sum of this geometric series, if you need a reminder, let me know. It's the constant term divided by 1 minus the term that is being exponentiated here. Don't simplify anything, that's why I didn't subtract, it's no use. Then I multiply top and bottom by 36, look at it. And what did I get? I get 5 on the numerator. Here I have 36 minus 5 minus 3, which is 36, they are canceled. It's 5 over 5 plus 3, 5 over 8. How many of you scored? So many of you said 1/2. How many of you said the right answer? 1 person. Kazi answered this correctly. Everybody else did not answer the question correctly. Kafka protocol, my friends, right? Don't be high-nosed. with Kafka protocol, right? If you're reading Kafka, you understand what I mean, right? Why did I pick it? It's because you cannot be right with probability. It's just impossible, right? That's the idea why I call it Kafka protocol. And it's all about bureaucracy. Okay, now do you understand how I did the infinite series, guys? How did you solve it? How did you get 1/2? I wonder. Would anybody let me know what was the 1/2 about? How did you get 1/2, guys? Let's talk. Valeria, you look like
I just thought it's common sense. There are two options, and it's either one option or the other option. But I kind of missed on how many chances to get one option or another.
Well, yes. So you understand one option or another. That's a very funny type of reasoning. I mentioned, right? Either you get $1 million today or you do not. It's there are two options, right? But it doesn't mean they're equally likely. Yes.
Yeah.
Yes.
I even thought, oh, that's an easy problem.
Maybe
I thought it's an easy problem because it's common sense. Two options, one or another.
Yeah, so it is common sense,
easy.
but because you know that's expected value. That's chapter 4 where you call common sense, right? So yeah, probability, guys. You know, if you learn German, for example, I will show you. Oh my God, there's such interesting lectures. I'm not sure they are there, but I was listening right now to Heisenberg's students lecture. He has whatever it's called, the Alternative Nobel Prize, and he speaks about quantum physics. And it's entirely, I mean, I understand nothing of quantum physics, but I do understand whenever he makes references to probability, right? So everything is probability from that perspective. Good, so yeah. That's again my futile attempt to try to make you learn another language, maybe German, maybe Russian. So I can do it. Kazi, by the way, would you like to say how you got 5 divided by 8?
Yeah, sure. I mean, my method wasn't as sophisticated as yours. I literally just listed the entire sample space and counted the possibilities.
But that is much more sophisticated than what I did. And I'm going to actually say below. Just because you used a simpler way of reasoning, it makes it actually better, right? If you're having complicated machinery, it doesn't make it smart, right? If you answer it efficiently, that's actually much better than what I did. So when I was introduced to this topic, that's immediately what I thought. I thought infinite series. But then later, actually, through interaction with some students, I realized, well, I can actually do it much better, just like what Kazi did. And here is how this problem can be solved. So this problem—
Can I ask a question? When you listing sample space, how do you know you're done listing? Because I never list everything. I always forget to list them.
Well, I see usually sample space contains way too many things to list them, but I try to keep account or try to know or keep track of every single thing that is there, right? Not to let it slip from my eyes, as you say. Okay, so in this case, I can actually list it. But in other situations where there are many outcomes, I cannot list it. I cannot list all the outcomes. Perhaps I can still count them without listing them, though. Okay?
Yeah, I always avoid listing because I keep missing on a few
Sure, but you see, you have to. That's why you have to have a bureaucratic way of doing it, and unless you have a definite way of avoiding making a mistake, then you will usually make one. So here is what Kazi possibly observed here, is that notice that the game is equally likely to end in any of the outcomes. It doesn't. It's not allowed to end until either sum 8 or sum 4 comes to existence. Correct? And if you just use your intuition, then you think there is no preference to any particular outcome, right? Because the dice are fair, they don't prefer any particular pair of numbers over any other particular pair of numbers. So they would not care which of the 8 particular numbers will be selected or the sum that results in 4 that will be selected. So it will be 5 possibilities in the numerator because it has to be 8, and 5 plus 3 possibilities for the sum to equal for it to be either 8 or 4. Of course, you cannot make this following objection. How do you know the game is going to end? Maybe one possibility that you are forgetting, Kazi, is that the game might continue forever and never terminate. Yes, can we eliminate that possibility or not? Okay, so with the infinite series, that possibility is not a challenge. But even with this method, you can argue away that with probability 0, the game continues to be going forever, which doesn't mean it doesn't, right? It just doesn't mean, it means that if you play it, it will be rather unusual. Good. All right. And some people avoided giving me the answer, right? So yes, some very particular, rather small people avoided giving me the answer for this particular problem, right? Now, part B, that is to solve this problem in general. Let's see if we can do that. What's the probability if the sum 4 is replaced by an arbitrary sum S, and 8 is replaced by some arbitrary sum T? You understand? And what's the probability that T appears before S, where T and S are numbers between 2 and 12? And Bowen, you have been hiding from me. You speak Russian, right? Non-hiding. I need to see how well. Kazi, interpret, interesting what you're saying. Very nice. Except, well, be careful, since you're saying T over T plus S, that's just what the sum equals to. How many, be careful there. That's just the value of the sum. How many possibilities are there to get that number? What is that? So possibly, but you know, figure out how to calculate it, right? P of t, yeah, Kazi. I want a more appropriate solution to it, right? We'll do it together afterwards. Well, you see, Sandy Wu, you're saying T is the number of ways of sum on two dice to equal T. In other words, you're saying that there is only what, two ways to sum to 2. There is only one way to add to 2, for example, right? So you have to be careful. And Murishika, again, you say T over T plus S. That's not right. It's not that simple. In other words, guys, I'm asking it for all possibilities, not just for 4 and 8, but any two possibilities. Okay, I'll read the question. How do you feel about writing out all the possibilities? I would feel terrible about it, right? That's not what I do. I hate possibilities. I like when there's only one possibility. You know, like when you go to a Russian store, you would know it, right? In Soviet Russia, you just pick, there is only one item to pick, if at all any. That's great. Soon you will experience that too. All right, so here is the question, guys, right? So did you understand question 8 with 4 and 8, right? You understood how I did it? So I realized how to do it in two ways. One of them was the infinite series way. The other was this thinking, okay, the game will not be over until 4, the sum of 4 comes out, or the sum 8 comes out. So then I see how many possibilities are there for the sum 8 to come out. There are 5 possibilities for that. And how many possibilities for the sum of 4 to come out? There are exactly 3 possibilities, yes? Now, each of those values will be the end value of a game. And the game is so structured that it does not care which of those particular outcomes are the actual result, correct? So that's how we knew the answer was 5 divided by 5 plus 3, because the sample space of the termination values for each game is it can be thought of as consisting of 5 plus 3 elements, 5 of which give us a victory. So it's 5 over 8. Good. Now, what's the situation for general S and T? So instead of 8, I have T, and instead of 4, I have S. Good. The question understood for you guys? Clear?
Professor, just correct me if I'm wrong. The main reason why T over T plus S wouldn't work is because we're looking at it as the sum and then the variable name, not because we're not looking at it in terms of the element, correct?
The reason T plus S doesn't work because S is the sum. Sum equals to S, yeah. Right?
And
sum
you want
equals
to look
S.
at
How many possibilities for that particular S? That's what we need to know, right? It's not S, right? For example, to get a sum of equal to 2, there is only one possibility. not two possibilities, right? So you cannot use S for both the sum and the number of possibilities of obtaining that same sum. Clear?
Yes, thank you.
Sure. And you, Melissa, you came slightly late. Is it clear? The part A clear? And part B, do you see what we're trying to accomplish? Wonderful. Okay, let's see. Yes, essentially, Murshika, you're correct. That's the idea. But then how do we figure out X and how do we figure out Y? Aside from that, you're absolutely correct. How are we doing there, guys? Ready for the solution or still thinking of it? All right. All right, guys. So what? One more minute, and then we'll reveal. No, I'll reveal my solution. So guys, if you cannot solve it in general, let's see if you can solve it for, let's say, numbers 3 and 10. I don't know, right? Just pick two numbers and see if you can figure the solution for them and how you carry it out. And of course, I revealed this. Well, not Kazi did it, I think, right? And can you also do it using the infinite series? Do you understand the infinite series argument? All right, guys. So I suppose let's do it together. Yes, ready? So here is how I think of problem B. So let's set up our equations. Let X denote the outcome on die number 1 and Y denote the outcome on die number 2. Good? So how many ways are there to get the sum equal to T? We have this equation. We also know that X is an integer between 1 and 6 and Y is an integer between 1 and 6, correct? So we are solving this equation and we want to know how many solutions are there. Well, clearly first equation implies that Y equals to T minus X, correct? And therefore T minus X must satisfy that it's bigger or equal to 1 and less than or equal to 6. So far good? And then I then see what is the restriction on X. So that means if I multiply everything by -1, -1 is bigger than or equal to X minus T, which is bigger than or equal to -6, correct? And then I add T to both sides, and that means that T minus 1 is greater than or equal to X, and X is greater than or equal to T, why did I put minus X? I meant T minus 6. That's a typo, yes? You see it's a typo, yes, guys? Should be 6 here. No problem. I hate typos, but it's okay, it's written, right? So that means X is between T minus 1 and T minus 6. Agreed? You're not confused by this line, guys, yes? I mean, just after you have this idea, it's just basic algebra. And then X simultaneously is between 6 and 1, correct? So what must X satisfy? It must satisfy both of those inequalities simultaneously. That means that X must be less than or equal to the minimum of those values. So minimum of T minus 1 and 6 has to be bigger than or equal to X, and X has to be bigger than or equal to the maximum of those two numbers, because if it's bigger than maximum, it's bigger than both. And if it's bigger than both, it's bigger than the maximum, correct? So this line contains within it both equations. You understand? And now I see where x varies. You understand? Once I know x, the second value y is determined. It's t minus x, correct? I just need to know what x is. Good? So what is the number of elements that add up to t? Well, it is the biggest number minus the smallest number plus 1. Do you follow why I do plus 1? So for example, if the possibility there isn't plus 1 is that you see here I take the maximum value and I subtract the minimum value that x can equal to. But if I don't add 1, then I'm not allowing x to equal to its minimum value. Right? You understand? It's just basic. It's a basic type of algebra here, right? So, for example, how many numbers are there between starting from 3 and going to 8? Starting from 3 and going to 8. So I take 8 minus 3 plus 1, or 8 minus 2. There are 6 possibilities because I mean to include the number 3. You follow why there is a plus 1 here, guys? Correct? So this is what it was. So for example, how many ways of obtaining sum equal to 10? Very simply, it's minimum of 10 minus 1 comma 6. So the minimum is 6 minus maximum 10 minus 6 and 1. So that means it is 6 minus 10 minus 6 is 4 plus 1. Okay, 6 minus 4 plus 1, which is 3. So there are 3 possibilities of getting sum equal to 10. Good. So, and you can just verify. You can verify that. So then afterwards, I do the same as what Morosika suggested. I just say A is the number of ways of getting sum of t, and B is the number of ways where we expect to get the sum. The other sum, the sum S, and so the answer is A divided by A plus B, where you don't need to list anything. You can just use this formula, which if you think about it, pretty easy to establish it, and then you know that answer. And here is the infinite series approach to this particular question. Yes, so the infinite series approach is that En is the probability here that I win the game on stage n. In other words, I get sum equal to t on stage n. So if I know the number of ways of doing that, it's going to be 36 minus a minus b. That means I have not won or lost, divided by 36 to the power of n minus 1 times the number of ways of winning divided by 36. And when you calculate this infinite series, you all know how to do this calculation, right, guys? I gave review for that at the beginning of chapter 2. And if not, we can practice. It's very, very easy to calculate it. So then you just simplify it and you get a divided by a plus b. So you get the same exact thing as you did initially without using infinite series here. Good? Clear? So naturally for this problem, I would have preferred the non-infinite series approach, as it is easier. Except there is one minor difficulty, is that you have to account for the probability of the game not ever terminating, and it actually is going to be 0. But yeah, okay. So and every other outcome is equally likely to occur. Good. The next question is pretty interesting, and if you are a very mischievous person, you can actually carry out it experimentally. So what ways can you, what procedure can you use to calculate the number E? Okay, the number E. So the procedure I'm suggesting is, you know, if you live in Brooklyn, you can go to Williamsburg and go to a synagogue where, you know, you have a lot of Hasidic Jews. They have very similar hats, and let's say that they have a coat hanger where they place or a hat hanger where they place their hat. So what you do is you randomly shift the hat so that when they come and they put on a hat, they don't know if they're putting their own hat or someone else's hat. And by observing this, by doing it several times in several big synagogues, you can say total number of pranks divided by the number of times that nobody picked his own hat. It will equal to the number E. Isn't it interesting? It will be E, which is that number that you're familiar from calculus. Now we can explain why that procedure is going to work. Are you ready? You understand what I mean, right, guys? There was going to be later, I'm going to talk about, what is it, Buffon's problem, where you do a similar thing, but to estimate the number pi. Okay, so if you want to know what pi equals to, there is a very interesting procedure, but that will be at the end of this class. Okay, so why is that going to work? Let's see. So we have this this matching game. Let's see. So suppose you have n gentlemen, and the n gentlemen, they each of them has his own hat. If each gentleman takes a hat at random, the question is, what is the probability that no one picks his own hat? Let's see, how can we do that? I'll let you, do you want me to let you think about this problem? It's a bit complicated. I don't know how much time it takes to do it in real time.
I most likely won't be able to solve it, so it's okay for me.
Yeah, so I figure, guys, can I spoil your fun and solve it, or do you want to try? Because it's a bit unfair to ask you to solve it for the first time in your life in what, in 10 minutes, or I'm not sure, even in 20, right? If you could solve it in 1 hour, that's amazing. But if you could solve it even in 3 for the first time, that's pretty good, I think. Yeah, so I guess I have to explain, right? It's too bad. You see, I also, what you can do is, like, we can extend this lesson to an extra hour, and you can try for 1 hour, and then we can continue the lesson today. That's fine with me, right? I like when you stay with me, right? You want to go, but haven't I played you this music? I want you to stay with me. Yes? All right, so here is how I figure to solve this problem. Okay, so let E sub K denote the event that gentleman K picks his own hat. Then I want to calculate the probability that not a single person picks his own hat. That means that it's the intersection from k equal 1 to n of ek to the complement. You understand? Because gentleman 1 did not pick his hat, gentleman 2 did not pick his hat, 3, 4, etc. All of them did not pick their own hats, correct? So that equals to 1 minus that's De Morgan's laws, right? 1 minus the probability that one of them did pick their own hat. So it's pretty clear how you go from this to that, yes? Now I'm going to estimate, I'm going to figure out, not estimate, I'm going to figure out what is this probability, yes? And for that, notice the events are not mutually exclusive. Do you agree? E1 is not, if person 1 picked his own hat, that does not mean that person 2 does not pick his own hat, right? So they're not mutually exclusive. So we are using the exclusion-inclusion formula. Do you remember it? It's this thing that looks scary, but it's very simple. What it is that you add up the probabilities of each event independently, subtract all combinations of pairs, add all combinations of triples, subtract all combinations of fours, and you do that until you reach n. In general, that's what this is saying. It's minus 1 to the k plus 1. You see, when k is equal to 1, then it's minus 1 to squared, so that means you're adding. And when it's 2, then it's an odd number to the power of minus 1, so you are subtracting, correct? So you understand how this formula is going to work. And we are going to need to simplify it because we don't want to list every possible k combination, okay? And let's see how good you are at it. So if I fix some arbitrary k between 1 and n, this is just talking about adding up the k combinations, right? All possible k combinations of those events, right? So how many summations do we have here? Do you know? How many summations do we have here? Let me know in the comments. No. For a fixed k, first of all, how many summations do we have here? For some arbitrary, no, just k. So how many singletons, right? We have all the way from 1 to n. Singletons only n, right? How many pairs? So in other words, we have E1 and E2, E1 and E3, E1 and E4 all the way to E1 and En, and then E2 and E3, because we need to consider each intersection exactly once according to this formula. How many summations do we have? No, not k factorial. Come on, guys. Kafka protocol. Kafka protocol. You need a document and tell me with the document how many possibilities are there. You understand? What are you adding here? You're adding every possible combination, correct? So we need documents that attribute every possible k-fold combination. You understand what I mean by k-fold? So let's say how many sums of 3? How many possibilities of having 3 combinations are there, right? So you must have a document that indicates, okay, we have an occurrence of combination 3, or we have an occurrence of combination 4. So how many for combination k? Kafka protocol. How many pairs? It's only when you have 2, but in general, you need to consider for the inclusion exclusion formula how many singletons, how many pairs, how many triples can you have. You understand how the summation works, guys. You should really think deeply about the sum and understand how it functions. Okay, so I want to know how many terms is if I fix k, let's say equal to 3. How many 3-fold combinations do I have here? You understand? You have, let's say, 3-fold combination means person 1 picked his own hat, and person 5 picked his own hat, and maybe person 6 picked his own hat. Okay, how many possible? You understand? So imagine you have documents for each k. You have document that you need to report. You need to write a formal report, and you submit it to the ministry that lives in the castle, perhaps. Yes. You understand my question, guys? Yes. Okay, Shotaro, but not K. So how many for just K? So there are only one form. You see, we go through K1. We are adding them one at a time. Then we go K equal to 2. We see how many 2-fold combinations we have. Then how many 3-fold combinations. Simple thing, guys. What is a k-fold combination, right? That means what? That means I observed that k people pick their own hats, right? So then you say which of those k people pick their own hats. Yes. 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 All right. So let me tell you what it is. It's n choose k. Isn't that obvious? One. Well, how many possibilities if it's one person, right? Which person? Is it Jimmy? Is it Josh? Right? So you just list them by numbers. Each individual, gentleman 1 through gentleman n. And when you say EI1, EI2, EIK, it means that those people, I1, I2, IK, I1 indicates the gentleman with the smallest number, I2 indicates gentleman with second smallest number, etc. So how do you list them? You have a form that containing 4 squares, right? And you have to place information in those squares in order from smallest to largest. And that's exactly n choose k. Clear? Not clear? Not clear, guys? You're quiet. I have no idea. Clear or not clear? No answer, I guess not clear. Look at the summation. Yeah? So when I fix k, at that moment when I fix k equal to 3, I am considering this is going to be minus 1 to the power of 4. Yes, minus 1 to the power of 4. So we don't care about it. But what is this going to be like, right? So it's going to be 1, 2, 3, 1, 2, 4, 1, 2, 5, 1 or 2 all the way to n. And then we can update maybe 1, 3. Oh, I mean, yeah, 1, 3, and onwards, right? You understand what I mean? So how many possibilities are there? If it's 3, it's how many combinations of 3 individuals at a time? So it'll be n choose 3 possibilities. If it's if the sum is 4, so in general, if the sum is k of size k, then it's n choose k. And naturally, you agree that there is no preference in this problem which gentlemen pick their hats, correct? So if it's gentleman I1, I2, or IK, it doesn't matter. It's the same probability if they were 1, 2, and k, all the way to k, correct? So like instead of adding those terms, I can say it's the same as probability of E1, E2, EK multiplied by n choose k. I eliminated the sum because you see it doesn't matter which particular k individuals pick their hats. There is no preference for one set of k individuals over another set of individuals. I'm using symmetry here. Clear, guys? Yes, Naomi, it's clear to you. I mean, you look very thoughtful. I wonder.
I think so. I think so.
Okay, think so means it's clear, right? Or you're not sure whether it's clear or not. Yes, it's either clear or not, but you're not sure of that. Yeah. So we have this situation, right? We have n choose k times this probability. Now, can you calculate this probability that exactly that those k people pick their own hat? It means that numbers 1 through number k are taken, and we have an additional n minus k numbers available to us, yes? And they can do whatever they like among themselves. So there are n minus k factorial possibilities if I know that 1, 2, all the way to k pick their own hats, and the rest they can do whatever they like, right? So there are n minus k factorial possibilities. Total possibilities obviously n factorial, right? Because we can say hat 1, hat 2, hat 3, and onwards, right? All the hats. And then the individuals underneath them, they are ranked also by numbers 1, 2, 3, and onwards. Good? Good? So that is how we get n minus k factorial over n factorial. Everybody is with me, guys? And so now I can begin simplifying things. What is n choose k? It's n factorial, k factorial, n minus k factorial. And look at that. We cross out the n factorial. We cross out the n minus k factorial. We're only left with k factorial. And so this sum all the way to n is minus 1 to the k plus 1 over k factorial. Yes? And that's the summation. Why is it, this is the minus 1 to the k plus 1, right? And then what do I do with it? Now, the probability I want is 1 minus this number, yes? When I take 1 minus that number, that's the same as 1 plus the summation where it's minus 1 to the power of k. You agree? Because I can move an extra minus 1 in here, and that's k plus 2, and the 2 doesn't matter. I can just say minus 1 to the k. Yes? Some of you look pale, look like blood is not getting into your brain anymore, right? Is it clear? Maybe hang upside down, it will help. And so what is 1? 1 is also minus 1 to the 0 divided by 0 factorial. And so the answer is k0 to n of minus 1 to the k divided by k factorial. Does it look familiar? Is this thing familiar to you? What
that's
what
E,
is that?
right?
This is it, what is the number?
E?
No. E is bigger
It's
than
1 it's 1 over E, right?
When an n goes to infinity is 1 over e. Exactly, Shotaro. It's e to the power of minus 1. Right? So if I take n to infinity, this becomes the infinite series from 0 to infinity of minus 1 to the k. Remember, if this is x to the k divided by k factorial, it's e to the x. So we have minus 1 here. So it's e to the power of minus 1. Yes? And that's where I mentioned that it ends up being, it's not coincidental and it's not arbitrary. So it's a kind of, it's something we will see in chapter 4 more of. Yes, in the Poisson paradigm. And so you understand, so it means that what? It means that if I do this experiment with many gentlemen over and over again, I will see that the number of times they don't pick their hats over the total number of games I played is approaching e minus 1, which means that if I reverse it, if I say total number of pranks divided by total number of times that nobody picked their own hat, it will be the number e. Of course, there is no reason to do this estimation because we already have a very nice series here that will estimate what e is, because e would be, just plug 1 here. It would be 1 to the 0 divided by 0 factorial plus 1 to the 1 divided by 1 factorial plus 1 to the 2 divided by 2 factorial. Understand, right? So you already have a good estimation of it, so there is no need to do that. For pi, there is something pretty cool. Good. Now let's do the next short quiz on probability. Let's see how well you know this. Okay, so come on guys, a closet contains 5 pairs of shoes. If 3 shoes are randomly selected, what is the probability that no complete pair occurs? You understand? You have 5 pair of shoes. It's a homage to somebody I used to know a long time ago, right? There was this Polish girl, she loved shoes. I called her Shoe Polish. Right? She would buy shoes every time. Anywhere we went together, she would buy shoes. And once she passed by the embassy and she looks at the flag, and says, red and white, blood and tears. And I look at her and says, yes, of the Jewish people. Right? So that is pretty much what this reminds me of. So go calculate this probability. Okay, Kazi, you said something there. So 51 over 56 over 81, you say. You might have made a mistake, I think, but we'll wait. So, yes, let's see. Yes, interpret, I see that. Alejandro, good. Naomi, okay. Let's see what it is. Okay, yes. Okay. Just name. Yes. Okay. Yes. Good. 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 Okay. Let's solve it together. Good. Yes. I think most of you figured it. Okay. So how do we do that? Well, first of all, imagine assigning every shoe a number 1 through 10 through. Yes. So assign the number 1 through 10 to each shoe. Correct. And then we need the sample space is choose 3, right? 10 choose 3, pretty much, right? And then you can do the following: assign each pair of number 1 through 5. So you have pair number 1, pair number 2, pair number 3 onwards, and then within each pair designate shoe right, shoe left. Okay, right, left, or 0, 1, or whatever you like calling it, right? To designate the shoes. So then here is the protocol that I have in mind. Okay, so the protocol is shoe the pair number that was selected. You see, I like to draw those dashed lines to indicate that you have to put them in order. Good. And when I put solid lines, I mean it's independent box. It's an independent experiment. Right. So this would be the pairs, and for each pair I decide left or right, because I cannot have a complete pair. Correct. So how many possibilities? 5 choose 3, 2 cubed, right? So it's this number, which when you simplify, it's 2/3. Okay, you can see what is 5 choose 3? It's 5 times 4 times 3, and then you have 10 choose 3. You can do the 3's cross out, so you just have it in order. Then to do the cube, you know just what you can do afterwards. It's simple, right? Now, what is the probability of B? Exactly 1 pair. So the second part, exactly 1 complete pair, yes? Very good thinking, interpret. Very good. So you can do it very fast, but also solve it the slow way, just in case it's the one problem, right? Because you're training to use the protocol or thinking in terms of the protocol. Good. Always, guys, so when it's on the exam, if it's on the exam for the, it would be nice if you write me the protocol so I see how you are thinking, okay? And for yourself, you can decide. You can do it in your head or you write it on paper, but only when you are good at it, right? Okay, Naomi says 5 times 8. Naomi, careful. So we say 5 times 8. Why? Okay, you're saying one pair, and then there are another 8 possibilities. That's good. That's good. Yes. Okay, so let's solve it. Obviously, the answer is 1/3 because in light of problem number, what was the problem? I forgot, right? Problem number 8. Sorry, then we know that we calculated not having any pairs, right? Now you can either have, there are only 3 shoes selected, so you either have one complete pair or you have none. So the answer has to be obviously 1/3 from it, right? But here we can do it from scratch. This is from scratch. So this is the argument as one of you suggested, 1 minus 2/3. And then the other is doing from scratch. So here is the pair number. Naomi did the same way as I did. Pair number, and then remaining shoes, right? So once I know the pair number, it also eliminated. I have only, it eliminates, if I know the pair number, it eliminates particular 2 population shoes, and I'm left with 8 possibilities here. So that must be correct, and it gives us 1/3, right? And so the answer has to be 1/3. If it's 1/3, then calculate it for yourself, right? Then you're right. Next question is, here is the next question, guys. 7 students, student 1 through 7, are seated in a row at random. What is the probability that exactly 3 students are seated between student 1 and student 2? Question understood? 7 students between student 1 and student 2. We need exactly 3. How many? What's the probability that happens at random? And yes, and yes, I think, okay. So so always, guys, you see, so that it doesn't take me long to figure out what you're doing. But yeah, Furby, you're right. Good. Right, just running. You have to be careful, Kazi, right? You're assuming in your sample space that it's equally likely that 0 or 1 or 2 or 3 or 5 or something like that will be sitting. I think I need to consider it. See, guys, when you submit your answers, here it's okay, but when you submit your answers on the exam, you will make it much simpler for me to understand your reasoning if you write it out, if you tell me what protocol you were using. Let me just do factorial. All right, let's solve it together. So here is one protocol. Naturally, you can come up with others, right? You have to just be extremely careful, okay? When you are modeling something that's not exactly the sample space, you have to really reason, is there a preference to that or not? Based on this information, we're aligning people in a row. So I have persons 1 and 2, and then I have persons 3 and 7, right? Altogether 7 people. So what I will do is how am I going to form my cluster? So I need 3 people, right? So first of all, the way I form my 3 people between 1 and 2 cluster is first I will say who is to the left and who is to the right, right? So does it begin with person number 2 or begin with person number 1? So there are exactly 2 possibilities of filling this information, right? So it's 2 factorial possibilities to list this out. Or you could have, I mean, I wrote 2 boxes. It's easier to write 1 box, just the box first person or person number 2, yes? They're not independent. So there are 2 possibilities here. If you should erase it, it should be 1 box, maybe write 1 and 2, right? Who is on the left? Is it person number 1 on the left or person number 2 on the left? And then the people in order left to right that are between 1 and 2, here they are. There are 5 choose 3 possibilities, yes? And times 3 factorial ways of arranging them. And then this is cluster 1. And there are additional 2 individuals that are not listed because altogether this makes 5 individuals and there are 7 altogether, right? So they are now a human centipede. They are attached to one another. It's now one object and it's designated with cluster 1. So this 1 refers to all of them. Where do I find them? I find them between whatever I grouped as 3 and 2. Good? You understand how this is supposed to work? And there are 3 factorial possibilities there. So my answer was 2 times 3 factorial, 5 choose 3 times 3 factorial over 7 factorial, and the result is 1 over 7. And I'm not claiming that what I did is by no means me. You can be much more clever than I am. I'm certain I'm right, right? This is what we have, right? you might be more clever than me, but you are not certain that you're right, and I am certain that I'm right. That's how it works.
That's a really nice way of doing it.
Sorry?
That's a really nice way of doing it.
Makes sense?
I like that.
Yes, so that's how you do my questions. Okay, so you can come up with another. You think always experiment. You might think, oh, I know something much better, right? I know a much more clever solution. Make sure that you have one solution that you know for sure, and then compare your clever solution against that, right? So do it in several ways. And here in those boxes, I would say better bureaucratic document will involve only one box because it will be who is the left person, right? I just listed it as 1, 2, or 2, 1. You understand? That's how this box is made. Now, one last question, guys. Bear with me. It's about New York. So a New York driver is racing through a school zone at the neck braking speed of 26 miles an hour, right? Like I am pretty much driving, right? And if his house is located in position 7-2, you understand, you can only move to the right and up. Basically, you don't return. You move to the right and up. So there is going to be, so this driver is going to randomly choose to go up or down. He's going to go to his home. The question is, if there is a traffic light, or sorry, not traffic light, a speed trap at position 4-1, this is the position, what's the probability the driver does not get ticket? In other words, what's the probability the driver avoids this particular intersection? Questions clear? Wonderful. Wonderful for you. After my class, you can work at the DMV, all of you, right? Possibly. 1 second, we'll check. Ambient noise coming through or not? You hear anything from my end when I don't speak?
No.
Okay, good. What's the answer? Okay, okay, Kazi, I'll think about it. So we have saying it's what you're getting maybe closer to it, but careful. I think, Kazi, that you are wrong. Let me know when you're ready, guys. Almost done. Melissa, are you there? Alive? Everything's good? How are the problems? Make sense? Mostly very diplomatically spoken. When you are tired of waiting, you let me know, guys, okay? Otherwise, I'll just keep waiting.
Can we go over the answer?
And anybody has objections? Are other people still working about it? Or you want me to go over the answer now? What about the rest of you? All right, guys. Okay, so let's see. I'm ready. Well, I guess you're ready to leave me, right? You figure, well, the class is over, let's go. But class is never over. Don't. It's not a discrete math thing, you know? It just continues. So here is the solution. I did not bother writing Kafka protocol, but you can do it. Okay, so first of all, F, the event that he gets a fine. What's that event? It means that he has to pass through this point, which means that in the first 5 steps. You see, each step you decide whether to move up or to move to the side. You will have to make 2 of your decisions will have to be up. You agree? So for example, I can go here, and then let's say I can go up, and then I have to continue deciding to go straight ahead. Okay. So in the first 5 steps, first step, second step, first step, you can decide to go up or straight, right? In the first 4 steps, you must make 1 decision to move up, followed by the next, how many next steps? 1, 2, 3, 4, 5. Next 5 steps, you have to make 1 decision to go up again. So it is, this probability of getting a fine is 5 choose 1 times 4, what is it, 5, or is it what? 1, 2, 3, 4, 5. 5 choose 1 plus 1, 2, 3, 4. 4 choose 1. So it's 5 times 4, 20 possibilities of getting through the traffic light. And how many unrestricted possibilities of moving? We have 9 decision points, of which 2 of those must be up. Okay. Which means it's 9 choose 2. So total sample space is 9 choose 2. What is 9 times choose 2? It's 9 multiplied by 4. In other words, there are 36 total possibilities, 20 possibilities of getting a fine, right? So the probability of getting a fine is 5 out of 9. Good? Or 20 out of 36. And therefore, the probability of not getting a fine is 4 over 9, or 44%. It's more likely that he will get a fine than that he will not get a fine. Make sense? You see, you could do that with the. You understand? You just realize that that here we have decision 1, decision 2, decision 3, decision 4, decision 5. In those 5 decisions, he must make 1 move up, and then he is here, exactly 1. Right? Make sense?
Can you explain again why the sample space was 9 choose 2?
Because in the 9 decisions, which of those decisions correspond to which decision numbers correspond to moving up? So that's 9 choose 2. Because the sample space is how many pathways has he moved, right? So you move left. Or you mean you move left or right? So a sequence of lefts and rights decides exactly how you are moving, correct?
So then why is it 9 choose 2 and not 9 choose 7?
Well, it's the same. 9 choose 2 and 9 choose 7 is the same thing. You are focusing on the left, and I'm focusing on up. Right, just 9 choose 2 seems easier right away. Not easier, truly the same calculation, but seems 9 choose 2. I just write 9 times 8 divided by 2. That's why I choose 9. You see, so there are only 2 ups. You agree, guys? Only 2 ups that I have to execute somewhere. So, for example, if it's left, up, then up, and then all the others are left, it means I'm making this pathway, right? If it's left, 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 up, left, 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 up, I'm making this pathway. You understand? So I have a sentence of length 9 made of L and U, right? So that's how many such words can I have? How many words made out of 7 lefts and 2 U's can I have? It's 9 choose 2, where the U's are located. Okay, and how many of them correspond to moving through this point? That means that in the first 5 moves, in the first 5 letters, there is exactly 1 up, and then in the next 4 letters, there is exactly 1 up. Yes, because you have 4 letters and there is 1 up. Okay, so you are somewhere here, and then we're at 1 up. Good. So that concludes chapter 2. What we begin next time is chapter 3, which is conditional probability, and it is already high time to prepare for your first exam, right? We covered all the material for the first exam. I would like you to do several things, because you're not just passing this class. You want to know the material. I want you to go over all the exercises that I recommended for homework 1 for the chapter 1 and chapter 2. And you have two actual former exams, right? Posted on my website already. I would be very glad to discuss those questions with you. So make sure that you know it. And I will write your exam shortly, hopefully, right? So I'll write it, and when I do, I will let you know. You will know it. Any questions?
Professor, could you briefly repeat that? I was stepped out for a second.
No problem.
Sorry about that.
No problem. Again, so we covered all the material for exam 1. It covers chapter 1 and chapter 2. I would really like you. It's not necessary to survive this test. I'm just saying the more exercises you solve, the better you are at the subject. I would like you to go over all the homeworks that I recommended, homework for chapter 1 and homework for chapter 2, and definitely over my 2 previous exams. Like I taught it last 2 semesters, and I have 2 previous exams, 1 per each semester. I would like you to solve those exams as well. There are some cool problems that I would feel very terrible if you don't, if you do not do them. I just feel, oh my God, it's such a nice treasure. What? Are you, yes?
Yeah, that's okay. And did you say like when the exam is going to be?
My God, it's a take-home exam, right? Well, how bad can it be?
Oh, it's a take-home exam?
Oh, no, yes, it is a take-home exam, right?
Okay.
Right? I hope it doesn't make you too glad and not want to study the material, right?
No,
I mean,
no, of
I'm
course
assuming
not.
that you guys are here because you love the subject and you don't give a damn about exams or about time that we were supposed to finish, right? Be it today, tomorrow, through the night, you don't care, you love it.
Of
Yes?
course.
Good. We'll see, right? Once I see people, if I see people dropping, then I will start my Russian exams. You don't need to do homework for me. You need to do them for you, for yourself, and we can discuss it in office hours. We can discuss your solutions for exam 1 and the exam 1 for 2nd semester and everything else. Okay. Have a good one, guys. If you want to stay and talk to me, stay and talk to me. We can do more problems.
Good night, Professor.
Okay, I understood your answer. Good night.